Hi, I'm Liliu, a graduate student in Dr. Babicheva's group in the ECE department at the University of New Mexico. I'd like to introduce a tool developed by our group that helps users simulate the effects of electron-beam exposure for different array periods and substrate materials. This tool is freely available to the public on nanoHUB.org, which is a science and engineering platform funded by the NSF. It offers community contributed resources and is designed to support education, professional networking, and interactive simulation in nanotechnology. Before we dive into the details, let me begin with the motivation behind our work. Electron-beam lithography is widely used for the fabrication of periodic nanoscale structures and metasurfaces because of its high resolution and design flexibility. However, the proximity effect and substrate charging caused by electron scattering and accumulation are unavoidable and significantly impact dimension, accuracy, and uniformity of the patterning outcome. So, the dimensions of the nanostructures are highly sensitive to exposure parameters such as the beam current and dose, which influence the feature size and uniformity. Additionally, substrate conductivity plays a crucial role in charge dissipation. Insufficient conductivity can lead to charge buildup, causing pattern distortions. These factors, in turn, impact the reproducibility and the consistency of the metasurface's optical response. Calculations performed with our tool can provide insight into how EBL exposure affects the lateral dimensions of the nanoantenna and reveal the impact of substrate conductivity. The tool also highlights a saturation effect, where the nanoantenna diameter stops increasing when the array becomes too dense. This tool offers a straightforward yet effective method for predicting EBL outcomes, enabling optimization of the fabrication process. Using this tool, you can calculate how the ZEP520A resistor responds to different exposure settings and layout configurations. This video will cover the tutorial for the tool that uses the distinct exponential relation between the exposure dose, which corresponding to the horizontal axis, and the nanoantenna diameter, which is on the vertical axis, for substrates made of undoped silicon, 1 micrometer thick silicon oxide on top of silicon, and fused silica. The availability of these three common substrates enables researchers to address distinct application needs, such as semiconductor devices, integrated optics, and waveguide devices, as well as UV visible photonic applications. Now, let me provide more detailed information. By searching for nanoHUB.org, you can see a user interface. I have already logged in and have been navigated to the tool launching page through my nanoHUB homepage. You can also find the tool through searching here by put NANOANT, which is the abbreviation of our title. And you can find the tool here. You can also click Add Modules at the top right to customize your interface with the modules you would like to display. Now let's dive in as I walk you through the tool's key features and functionalities. After clicking Launch Tool button, it brings up to the simulation interface. Once launched, the session begins. We will go through each option one by one to understand how the tool works, how each function does, and what the outputs mean. Let's get started. Here you will notice a schematic that illuminates nanoantenna diameter and the period parameters of the square array. The selection of the electron-beam resistor is ZEP520A, a commonly used positive tone electron-beam resistor in nanofabrication, chosen for its high sensitivity and superior etching resistance compared to PMMA. This enhanced etching resistance helps maintain pattern integrity during aggressive etching, enabling the fabrication of high aspect ratio nanostructures. You may also notice some default settings already in place. If you hold the cursor for a couple of seconds next to each of the options, a short note will appear next to it. It serves as a guide for the user on the parameters. The nominal diameter of the nanoantenna used in the setting defining electron beam exposure is 250 nanometers. The exposure depth ranges from 200 to 675 microcoulomb per square centimeter, with 200 microcoulomb per square centimeter being the minimum dose at which nanoantenna constantly appear in the patterning. The dose exceeding 675 microcoulomb per square centimeter will lead to the saturation and potentially overlapping of the nanoantennas. The array period in our tool spans from 300 to 400 nanometer in increment of 25 nanometer. To start the simulation, simply select the substrate material and the desired array period. The period is defined in nanometers. For example, you can choose a silicon substrate with an array period of 325 nanometer, then click the Simulate button in the top right. The tool will then generate the plot showing the relationship between nanoantenna diameter and the exposure dose for the selected period and substrate. Now let's look at the output plot. At exposure depth below 350 microcoulomb per square centimeters, the nanoantenna diameter increases nearly linearly with increasing dose. As the dose continues to increase, the diameter of the nanoantenna gradually approaches its maximum value. This indicates that further increase in dose no longer results in additional resistor exposure due to a dynamic balance between incident electrons from the beam source and electrons repelled by the accumulated charge. You can click the results and select the download option in the pop-up window to save the data as a test file for post-processing in the software and of your choice. Alternatively, you can click Keep for Later to save the session to your dashboard. The saved session can be found here from your session list. And for the nanoHUB, it allows up to 3 saved sessions for accounts of the standard type. You can also download results or manage simulations by using the question tab in the top right corner to save the current session or load previously saved ones. Additionally, you can review and ask questions directly in the tool interface or share the results through the link. Just by simply copy the link and share it with other users. If you want to cite or find a brief description of our tool, you can go back to the launch page, scroll a bit down to find the information. After watching this video, I hope you can add this tool to your favorites, and so you can get back to it quickly. Thank you for watching.